In this video, I'll show you how to run a trading strategy in QuantRocket. We'll use an intraday momentum strategy from Ernie Chan's 2013 book, Algorithmic Trading. This strategy uses leveraged ETFs, so first I'm going to retrieve all ETFs listed on ARCA and save them to my local database. This will run in the background, and I can monitor the logs to know when it's completed. According to the logs, the ARCA listings have been saved. Next, I download a subset of those listings to a CSV. These are the symbols for the leveraged ETFs I want to use. If we peek at the CSV, we see the trading specifications for our ETFs. Now I can use this CSV to define a universe so I can reference my subset of ETFs easily. I'll call my universe leveraged ETF. Now we need some historical data. Our leveraged ETF strategy enters in the afternoon and exits on the close. I'm going to try it with 15-minute data. First, I create an empty database that defines my data parameters. I'm going to name my database Leveraged ETF 15 Min, and I'll tie it to the Leveraged ETF universe that I just created with 15-minute bars. Now we can fetch the data from IB into the local database. This will run in the background, and the logs will tell us when it's done. I can look at summary logs as well as detailed logs. Now that we have historical data, let's research the trading idea from Ernie Chan's book. The strategy hypothesis is that if the leveraged ETF is up significantly by the afternoon, we should buy and hold it until the market close, anticipating that the ETF sponsors will need to buy the underlying assets near the close as part of their daily rebalancing, and this should drive up the price even further. Vice versa if the leveraged ETF is down significantly for the day. Let's start by pulling some historical data into a Pandas data frame. Provide the name of the database, and for best performance, I'm only going to ask for the bar times and fields I care about. Not so important with this small database, but important for large intraday databases. I'll attach a console to peek at my data frame so that I don't clutter my notebook. If we peek at the prices data frame, we see that the index contains the field, the date, and the time. And the columns are the securities represented by their unique contract ID, or CONID. The first thing I'd like to do is calculate the daily return from the prior close until 2 p.m. I'll use standard Pandas syntax to do this. I can use loc to locate a particular field. I use XS, short for cross-section, to isolate a particular time. The session close is the closing price of the 1545 bar. The bar times represent the start of the bar. The 2 p.m. price is the open of the 14 o'clock bar. Shift the session closes to get the prior close. Then we can calculate our prior close to 2 p.m. return. I'll take a quick peek at those returns. I call this variable factor because this is the predictive factor that we're hoping predicts forward returns. Let's now calculate those forward returns. The forward return I want to look at is the return from 2:15 to 4 o'clock p.m. The 2:15 price is the closing price of the 14 o'clock bar. Using that in the session close, I calculate the forward returns. To visualize whether my predictive factor works, I'll use AlphaLens, which is an open source package from the team at Quantopian. I need to format my data the way AlphaLens expects, and since this involves some boilerplate that I'll probably need to use in future notebooks, I decided to make a reusable helper function in another file. Here's that helper file and function with some boilerplate code. Back in my notebook, my helper module is importable using standard Python dot syntax. This helps a lot to keep your code organized. Great. Now let's import AlphaLens and get a tear sheet. And give that a moment to run. My factor looks promising. The lowest quantile has negative forward returns, and the highest quantile has positive forward returns. The cumulative return chart looks promising. Now that I've researched my trading idea, I'm ready to run a backtest using Moonshot. Moonshot is an open source pandas-based backtester that integrates tightly with QuantRocket. Because Moonshot is pandas-based, the transition from research to backtesting is seamless. You can develop your code interactively in a research notebook, peeking at your data frames as you go, then transfer the code to your Moonshot strategy. On the left side of my screen is my research notebook from earlier, and on the right side is the corresponding Moonshot strategy in a py file. A Moonshot strategy is any Python class that inherits from Moonshot. Give your strategy a code, which is how you'll refer to it in backtesting and live trading. I'm calling mine Intraday. Point your strategy to your history database and define any query parameters, just like in research. When you run a backtest, Moonshot will query your history database and pass the prices data frame to your prices to signal method. This method should contain your trading logic and return a data frame of signals, long, short, or cash. I've copied over my research code to calculate the 4 p.m. to next day 2 p.m. return. And for now, I'll go long or short when the return is plus or minus 2%. I may change that threshold later. I'll cover the next two methods quickly. You can read more about them on the website. Signals to target weights receives my signals data frame and should derive from it a data frame of target weights, defining what percentage of my capital to allocate to each signal. I'm allocating a fixed 5% of capital per signal. Target weights to positions receives my data frame of target weights, what I want to own, and should derive from it a data frame of positions, what I actually own. In this case, I'm entering the position on the day of the signal using market orders, so my positions are the same as my target weights. Finally, positions to gross returns receives my data frame of positions and should calculate from it a data frame of returns before slippage and commissions. I calculate the 2:15 to 4 p.m. return, copying over the forward returns calculation from my research notebook. You can backtest from the command line or in a notebook. I'll use a notebook. To run a backtest, pass your strategy code or a list of codes for a multi-strategy backtest, an optional start and end date, and save the backtest results to a CSV. Backtests run quickly since Moonshot is pandas based. There are several things you can do with the resulting CSV. You can view a performance tear sheet using Moonchart, an open source companion library to Moonshot. You can also create a tear sheet using Pyfolio, an open source library from the team at Quantopian. Moonchart and Pyfolio have some different visualizations, so it's nice to look at both. Finally, you can load the backtest results into pandas for your own analysis. Something I noticed in my Moonchart tear sheet was that my strategy trades quite a lot. The average allocation is 84%. That concerns me because I wasn't yet modeling commissions or slippage, and I'm worried that transaction costs might be too expensive if I'm trading that much. I'll use a parameter scan to help me figure it out. First, look at a few changes I've made to my strategy. I've defined a detailed commission class to model IB's tiered commission structure. You can define simpler commission classes, but this one will be most accurate for my purpose. And I've tied it to my strategy. You can run one-dimensional or two-dimensional parameter scans targeting any of your strategy's class attributes. I've added an attribute called slippage BPS, which is a built-in Moonshot attribute that lets you define one-way slippage in basis points. I've also factored out my hard-coded plus or minus 2% threshold into an attribute called min%change. These are the two parameters I'm going to scan. As with backtests, you can run parameter scans from the command line or in a notebook. I'll use the command line. Specify the strategy code or codes, optional date range. The first dimension for my scan is slippage BPS, and I'll test using 0, 4, and 8 basis points. The second dimension is min%change, and I'll use 2%, 4%, and 6%. I want to get back a PDF tear sheet instead of the default CSV. In the logs, I can watch as Moonshot quickly runs through each backtest permutation. Let's look at the PDF. 2D scans are visualized with heat maps, as well as comparative cumulative return plots and underwater plots. Looking at the heat map for compound annual growth rate, I can see that if I assume no slippage, I make more money using a plus or minus 2% threshold. But if I assume 8 basis points of slippage, I do better by setting a higher threshold of plus or minus 6% so that I trade less frequently. So I should probably do more work to figure out what my slippage will be. Now let's learn how to live trade my intraday strategy. I'll walk through the live trading steps manually, and in a later section show you how to schedule live trading to run automatically. You can think of live trading in Moonshot as running a backtest on up-to-date data and using the last row of your target weights data frame to create live orders. Here's the tail of my target weights data frame from an earlier backtest. If this had been run on up-to-date data, the last row would represent the positions I currently want to hold. For live trading, I've added a new method to my Moonshot strategy, order stubs to orders. This method receives a data frame of partially defined orders based on my target weights data frame and allows me to further define exactly what kind of orders I want to send to interactive brokers. For this strategy, I'm using smart routed market orders to enter my positions. I'm also attaching child orders to automatically exit my positions using market on close orders. I need to tell Moonshot which accounts I'll run this strategy on. I define that in this YAML file. You can run multiple strategies per account and multiple accounts per strategy. Enter your account number. I'm using my IB paper account, the strategy code, and the percentage of the account's capital to allocate to the strategy. I've chosen 50%. Now I'll bring my history database up to date by running the same command I ran for the initial data collection. This only fetches the new price history since the last time I ran it, so it runs much faster than the initial collection. I check the logs for status, and already done. Now I use the command line to live trade my strategy. Moonshot doesn't actually place any orders, but returns a CSV of orders which I'll place in a subsequent step. Let's peek at the orders. These are the order parameters I defined in my order stubs to orders method. Here are my market orders to enter positions, and my market on close orders to exit positions. Moonshot has calculated the required number of shares to achieve my target weights. Note the order ref column. This comes from our strategy code and is used for associating positions and executions with the trading strategy they originated from. Now I can place the orders using QuantRocket's blotter, which returns the order IDs. It's been a few minutes since I placed my orders. Let's check the order status using the blotter. I'll filter by order ref and ask for JSON, and convert the JSON to YAML for easier reading. My entry orders have filled, and my exit orders are being held in IB's system until the appropriate time. Now I'll check my portfolio. This command returns a CSV. Rather than saving to file, I'll limit the fields to fit in my viewing area and use CSV look to make it readable. This shows me the same information I would see if I logged into Trader Workstation. To automate live trading, I've scheduled the commands I ran manually earlier. Scheduling is done with QuantRocket's countdown service using standard Unix cron. You can run a countdown service for each time zone where you trade, so that you can schedule your commands in the local time zone of the exchange, and not get tripped up by things like daylight savings time. I'm running a countdown service called Countdown New York for my US strategies. This is the cron tab, which utilizes a simple naming convention. First, I've scheduled my history database to update each day just after 2 p.m., the first minute of the 14th hour, Monday through Friday. This will ensure that the 2 p.m. price is available to my moonshot trading logic. I don't need or want to update my database if the market is closed for a holiday, so I've added a conditional expression to check whether ARCA is currently open. The command will return true if ARCA is open and false if it's not. The double ampersand in shell syntax means that the second command will only run if the first command returns true. I've scheduled Moonshot to run at 2:15 p.m. each trading day, mirroring the entry time used in my backtest. Instead of saving the Moonshot orders to a CSV as I did to trade manually, here I use a Unix pipe to send the orders directly to the blotter for automated placement. I also have some maintenance commands related to this and other US strategies, which you can learn more about in the documentation. I've been running my trading strategy for a week or so, and I'd like to see how I'm doing. QuantRocket's blotter tracks your executions on a strategy-by-strategy basis. You can query your P&L details and plot them using Moonchart, just like a backtest. This can be done in a notebook or at the command line. I'll use the command line. P&L plotting supports multiple accounts and multiple strategies, but I'll look at just my intraday momentum strategy. I'd like a PDF tear sheet rather than the raw CSV. The tear sheet gives me summary performance statistics, cumulative return plots before and after commissions, and various other plots to help me analyze live trading.